Okay, so today I'm going to be talking about gravity, specifically Newton's law of gravitation. Okay, so with Newton's law of gravitation, he thought, well, because there's gravity on Earth, there must be the same type of gravity that is holding the moon in its orbit. This is when he came up with universal gravitation. So this is saying the force between any 2 points of mass 1 and mass 2, and these are both in kilograms, is attractive and has magnitude. So this is the equation we're going to use. So force equals G, and I'll talk about G in a moment, mass 1 times mass 2 divided by r squared. So r is the distance or the radius between two objects. G is our constant, which is 6.67 times 10 to the negative 11th. So an important part of this is that the gravitational force is always attractive, and 2 points along the line connecting the two masses is r. Okay, so we could really take any mass in any situation and figure out the force between the two. However, often the force is so small, it's actually something we don't even notice. So G is a very small number, so 6.67 times 10 to the negative 11th. That means the force of gravity is almost nothing unless there is a very large mass involved, such as the Earth and a person. So if an object is being acted upon by several different forces, the net force is the vector sum. Okay, so if we have a situation where we have a sphere and then some other mass or some type of body, okay, we have to remember that there's the radius of the actual object and the distance between it. So this is really important when you're thinking about problems. If it says something like the radius of a planet is 3 times 10 to the 6th meters, and then there's an additional distance of 9 times 10 to the 6th meters. We're going to have to add those two together to get the actual radius, those points between it. Now let's actually apply this to how we figure out weight. So if we're trying to figure out the gravitational force, aka the weight of an object on Earth, we need to kind of rewrite this equation. So the force is equal to the gravitational constant times whatever mass we have, maybe a person, times mass of Earth, divided by the radius of the Earth squared. And right here we pulled out this mass. Now, we can actually replace this force with mass times gravity, which is our weight. And we can actually figure out that gravity is equal to gravitational constant times my mass of my Earth divided by the radius of the Earth square. Okay, so just a couple notes on gravity and acceleration. So the acceleration of gravity decreases with altitude. So if we are here, we're probably about right here, okay? As we get higher and higher up, my gravity is going to get smaller and smaller. But we really notice this change isn't too drastic at this point. Maybe it went from 9.8 to about 9. However, as we get farther and farther out, the gravity is going to exponentially decrease. So when we're all the way about 20,000 miles out, we really don't have any gravity anymore. We are almost too far away from Earth for it to actually make a difference. An equation. So let's say that there is a mass of a 70 kilogram boy, and he's standing at sea level on Earth. So let's draw this. So here's Earth. Actually, let me make that kind of look like Earth. So here's my water. And then let's make some land masses. Okay. And then I have my little boy who is standing up here. Actually, he's not really little. 70 kilograms is like 140 pounds. So he's staying on Earth. And something we can look up, and actually it's pretty good to write down, is that the mass of the Earth equals 5.98 times 10 to the 24 kilograms. Sorry about that. That should be 24. And then my radius of the Earth is equal to 6.38 times 10 to the 6th meters. Okay, so these are something that we have. We can look it up, and it's given on your AP exam. So we need to figure out what is the force on the Earth and the boy. So we can use F equals gravity times m1, m2 over r squared. Now from here I can plug things in. My gravitational constant, 6.67 times 10 to the negative 11th. And then I have 70 times my mass of my Earth times 10 to the 24 all over 6.38 squared. Oh, sorry. What did I forget? I almost forgot the times 10 to the 6th. So actually it's kind of cool I made that mistake because that is a very common mistake I see in these problems. Sometimes big numbers can really mess us up, so make sure when you're doing this with your calculator you're going a little bit slower. Now, from here I can work this out on my calculator and I should get 685.54 newtons. Now, what we know from the previous slide is that my force should equals mass times gravity. So my mass of the boy is 70 times 9.81. So I get just around there 686 newtons. So we kind of proved our point right here that through the gravitational constant we can also prove that this is also weight.